Let's start with some review about introduction to logic gates. And I'm providing chapter number 3 of this first reference and chapter number 2 of the second reference on Canvas, so you can follow the material at your own pace if the slides are not enough. Some learning objectives and introduction. We'll start with the brain of the system. It's done by using computers, and inside of computers we have digital logic, and we have these binary numbers or base 2 of information being exchanged between ICs. We can also use different bases like base 8 octal or base 16 hexa to condense that binary information. We have a different way of representing text and numbers, BCD and ASCII, and we know that inside of those ICs, to manipulate this binary information, it's based on a set of addition and subtractions, multiplication and divisions. But how can I represent binary numbers with hardware? What's inside of this black square that allows to represent information with binary numbers? Well, this black square, again, it's what we call integrated circuit, and we have inside what's called digital circuits. What are digital circuits? Well, digital circuits are electronics that can handle digital signals, so 0 and 1, or 0 volts and 5 volts, and are done by using resistors, diodes, transistors, and a bunch of electronic components. We have normally two states, one near reference value, typically we not call it ground or 0 volts, and another one near the supply voltage. And we have this concept of on and off, so switch open and switch closed, so true or false. And how can I build a circuit that behaves like this switching, opening and closing, so I can have this 0 and 1, this binary information inside of my digital circuits? Alright, so if you recall Intro to Mech 1, let's do a little bit of reverse engineering. And let's open the top of this IC, let's peel it, and this is what you see, a bunch of wires connecting something that it's here to the outside pins, the pins that we can see and have access. Let's zoom in a little bit more, and I see things like this. What do you see? Well, I literally see just a bunch of squares and rectangles. Whatever I see, the scale is 843 nanometers, so times 10 to the minus 9, so very, very, very small. How small? Well, if this is the human hair, we're talking about something at this scale over here, so it's very, very, very tiny components. So what you're seeing is a bunch of diodes, resistors, some sort of components, electronic components connected together that they do circuitry. So some of these components we learned in Intro to Mech 1, resistors, diodes, LEDs and transistors, outside of the scope for Intro to Mech 2, so no need to freak out here or get overwhelmed, we're just reviewing. So we have millions of resistors, diodes and transistors connected together that represent these digital circuits. That's what you see inside of those ICs. So let's look at the basic digital circuit. It all starts with a transistor, and we have different types of transistors. In this case it's called a BJT, and a BJT has 3 pins, a base, a collector and an emitter, and we have 2 flavors here, NPN and PNP. It's just the way that these transistors are built. The one that we're going to focus is the NPN, which is this exact one that you see over here. And here you have a connection example. We have the transistor, we connect a set of resistors around the pins of that transistor, and we have our input and our output. So now this transistor is going to have some operation modes. Saturation means that the transistor is fully on, fully working. That's representing VCC, it's something that has always power. And if I have a 1, what's going to represent is that this switch is going to be closed. So if this switch is closed, my output now is going to be 1. So imagine a line connecting C and E together. when depending on the voltage that I put at the base. So if I put a voltage at the base, closes the switch. If I don't put a voltage at the base, the switch is open. So it allows or not for current to flow between your collector and emitter. There is a different configuration that we can do, and before we go there, so if I open the switch, is in this cutoff mode, so it's false, it's 0. This is another example. Now I switch the output. Instead of being connected to the emitter, I connect to the collector. And now the interesting part is that when my switch is closed, when I actually have this closed, my output is going to be off, and when my switch is open, my output is on. So it has the inverse behavior than what you just saw on the other configuration. Alright, this is what we call, it's an inverter or a NOT gate. So whatever I put here on the input, I get exactly the inverse on my output. And there is a way of representing that information using a truth table, where A is my input, F is my output. I only have one bit, so 2 possible configurations here. And if I have a 0, I get a 1, and with a 1, I get a 0. Alright, so if we connect transistors in different ways, we can get different behaviors. So we can build more gates, different gates. So if I connect 2 transistors this way, and now I have the power of turning on and off these transistors over here, I can build kind of a table here. If both switches are on, my output is if both switches are open, my output is 0. Then if I close one, I still have 0. If I switch, I still have 0. But if I connect both of them, so if I have a voltage going on A and B, these 2 transistors are going to be saturated, closed, and this voltage is going to show up on the output, and you get a 1. So I can write the truth table of this, and what I get is now I have 2 bits, 4 combinations, 2 to the power of 2. So for a 0 and 0, I get a 0, 0, 1, a 0, 1, 0, 0, and a 1, 1, I get a 1. And this is your AND gate. All digital devices, no matter how complicated they are constructed based on 7 basic logic gates. We saw the NOT gate, the inverter. We also saw a buffer. And we have the AND gate. We saw these 3 circuits. We can have an OR gate, exclusive OR, NAND, and NOR gate. And we cover simple addition in binary last week. And now if I have the truth table here, and if I want to perform the respective addition of these binary numbers, I get 2 outputs. I can have as many outputs as I want. In this case I have 2, the sum and the carry out. And now it makes a little bit more sense, the gates that I'm using. The AND is going to be your carry out, and the exclusive OR is going to be your sum gate, summation gate.